Yeah, so unfortunately I had technical problems and I didn't know that I will recover, but I did just the last minute. Yeah, so today I'm going to talk about the atmospheric response of those exo-Earths. And so my topic is I want to explore the scenarios of the atmospheric escape from Earth-like planets around M dwarfs in the habitable zone. So because the escape from exoplanets in habitable zones around M dwarfs, the most populous stars in our galaxy, is a matter of the atmospheric evolution, and atmospheric thickness plays a very important role in setting the temperate climate and habitability. So then I will talk about the ion escape from N2O2 Earth-like atmospheres using the results of our exogitum simulations, and then explore at what, and that's so the I can talk about the XUV-driven escape, photoionization escape only, so no other effects. And then transition to hydrodynamic escape at what XUV fluxes we would expect the transition from ion escape to hydrodynamic escape, and then explore the role of magnetic fields and the role of Joule heating with respect to the XUV flux, and then application to Proxima B and TOI 700D. So over the last about 20 years, and since the first observations and the Kepler observations, we observed so many exoplanets, over 4,700, and most of them are close-in exoplanets. They are pretty close to their host stars, and so 20, 30 times closer than we are to the sun. And given that most of the stars are magnetically active, so the question is that how those conditions are detrimental or favorable to habitability. So what you see here, that the TRAPPIST1 system, the famous system of 7 dwarf planets, can be easily fitted into the Mercury orbit, and the representative distance to a planet host is about 0.03 to 0.05 astronomical units, or 20 or 30 times closer. So we would imagine that if the star has the XUV flux of the comparable to our sun, that would account for a few hundreds of the XUV fluxes at 1 AU. So therefore, the question about how space weather in terms of the simple coronal emission together with the flare emission that produces much more enhanced XUV flux from the star, and associated coronal mass ejections and energetic particle events, that's called trinity, space weather trinity, can basically impact the atmospheric erosion and chemistry. So here we're gonna just start with the XUV fluxes, and here you can see that that we already know pretty much some fluxes from a pretty wide variety of stars from F to Ms, and they're pretty high fluxes. Most of them are either comparable to the current sun's fluxes or higher, given that the close-in planets are so at the distances 20, 30 times, that makes the fluxes, as you can see on the right panel, by a factor of a few tens to a few hundreds greater. And so given that also that M dwarfs, the low mass stars, retain magnetic activity, unlike our sun, for billions of years, that makes a big difference in setting the atmospheric escape, and the question of atmospheric escape of the paramount importance for the atmospheric evolution and habitability. So you can see there that the XUV fluxes can sustain very high even after the 5 billion years. So the one system that gives us some hopes, unlike let's say Proxima B or TRAPPIST1, it's the TOI 700 that was discovered by TESS recently. This is it has 3 planets, like Earth-like planets, And the star, as we did some calculations recently, the X-ray calculations with, simulations with nicer spacecraft, the X-ray flux is less than 10 to the 26 Earths per second. So the star is very old and inactive. So, and in case if the the regassing worked well, then we want to explore what's going to happen when the star is when the planet. So so this is basically the parameters of the 3 exoplanets. The 700B, C, and D, and the 700D is the planet at 0.16 AU, which much further than the typical exoplanets, close-in exoplanets. So I wouldn't call it exactly close-in with respect to others. It was a rotation rate of 37 days. And so we have calculated that the flux, XUV flux, expected flux, should be no greater than 10 XUV fluxes from the current sun. So this is basically the green zone of the deep exoplanet. And so therefore we want to evaluate the rate of of the escape driven by XUV fluxes. So we applied the 1D GITM code, the global ionosphere transfer model code that was developed to study our Earth. We extended it to exoplanetary environments. To the first we did the calculation for our Earth at 1 AU, and then enhanced the flux by 10 times to study the response, to compare with one time and 60 times, and see whether how the densities, temperatures, velocities will change. So, and we assume that the exoplanet rotates once in 24 hours, like our Earth. So here, what we see here, the black is the one, it's a current sun's XUV flux one time. So the red, it's 10 times, is the case of TOI 700D, and the blue one is the Proxima B most conservative case, so it's a 60 times. So, and we can see that the neutral temperature at exobase reaches up to like 14,000 kelvins for the case of 60 times, and reaches up to 10,000 for the case of the 10 times XUV fluxes. So I need to say that the low boundary is 100 kilometers. So we're talking about exospheric simulations, and so we're talking about mostly the layers at which the collisions are not very important. But if the heat deposition is high enough, then the pressure gradient probably gonna drive the much stronger winds. So here, what you see that this is the calculated M plus O plus escape, which is driven by the polarization electric field in the above the exobase. And so the Alex Glosser is going to talk a little bit more about it, and more general case of our planet ether code. But this calculations serve as a validation point using the code that was already validated for our Earth. So you see here, interestingly enough, that when the fluxes are low, then M plus to O plus the ratios can be at around 10 already can be comparable to O plus. M plus escape rate comparable to O plus, and that's consistent with what we see during large solar flares when the M plus escape rate becomes comparable or exceeds O plus, and for the 60 times it's goes all the way to 100 times. So the hydrodynamic escape rates, as you can see here, go by order of magnitude from 10 to 60 times. So, and the most curious thing is that at that point, when there's a 60 times, the hydrodynamic escape starts to turn in, and increasing the rays dramatically. So another important thing that we calculated the Pedersen conductancies, and you can see the Pedersen conductancies, especially at heights between 100 to 200 kilometers, vary by a factor of 5. And that's interesting that if we compare with the calculations of the parametric studies done by Ofer Cohn in his paper, 2018 paper, so we still can expect that the Joule heating for the Proxima B for those conductancies, it's a case, it's a green case, can still exceed the escape rate due to XUV emission. And the conclusion is that for the TOI 700D, the case of 10 times XUV photoionization driven heating causes 10 to the 4 kilograms of M plus and O plus escape, and M plus to O plus greater than 1. So this would be the case that will be important for the evacuation of the nitrogen rich atmosphere, the prerequisite for biology and for habitability. However, at 60 XUV fluxes, the rates become high enough so that we transition from ion escape to hydrodynamic escape. And so we're also starting to evaluate the role of Joule heating that can be a dominant factor of atmospheric escape for closing exoplanets with magnetic field when the wind is strong enough. So the one conclusion that we can make, that TOI 700D can have a thick atmosphere and that can be habitable. So of course, as a next step is we need to study also impact of CO2-driven cooling on the escape rate along with the NO, which is those two important cooling factors of the thermosphere. Thank you.
Thank you so much. I cannot see any questions in the chat right now, but thank you. Okay. We have a question from Karan Mulavardikani. He asks, how extended are the coronae of low mass M dwarfs? Wouldn't they engulf some of the ultra short period planets, for example, TRAPPIST1, B, C, and D?
Well, that's a good question. The point is that the coronae of those magnetically active stars, they extend into the stellar wind. So at some point, that the radius of fraction of this stellar radius, the coronal, the static corona, expands into the dynamic corona, and so we don't talk about corona anymore. We talk about the coronal wind instead. Yeah. So at that point, the stellar wind, the flow of ionized plasma basically interacts with the magnetosphere. So yeah, but yeah, in some cases the exoplanets can be found within the Alpine radius, which creates different scenarios that we're looking here. But for other close-in exoplanets, let's say TOI 700 or let's say Proxima B, those exoplanets are beyond the Alpine point or surface, I would say.
Awesome, thank you. We have another question. We have two more questions. One's from Shuanfei Dong, who asks, who says, you only show the density profile, but how do you know that if they will escape from the planets?
Well, unfortunately, I didn't show the velocity profile that will show that we calculated the point that at about 3 Earth radii, that's when the flow speed. Unfortunately, I don't have it here because it's only like 12-minute presentation. And we can talk about that later. Our velocity profile basically crosses the escape velocity from the star at about 3 the planetary radii. So at that point, that's when the atmospheric the hydrodynamic escape basically is most efficient. That will leave the planet. The gravitational will exceed the gravitational well.
Awesome, thank you. We have two more questions. One's from Kanako Seki, who asks, is there any indication that TOI 700D has a significant intrinsic dipole magnetic field?
Unfortunately not. That's what we would love to see. So we need some sensitive radio observations, and probably those observations can be taken from the moon, where the noise is, intrinsic noise is low, and to hopefully to find some decametric emission, auroral emission, due to if it had magnetic field, then of course the magnetic field, the strong magnetic field, the stellar magnetic field will interact with the magnetospheric magnetic field of a planet and cause the formation of eventual auroral electrons, which will create those radio emission. That we will expect that this effect should be strong enough. But it can only be done from the moon, probably, because of the low emission and the ionospheric cutoff frequency, which is around 10 megahertz or below.